Alright, let's talk about free body diagrams and how to illustrate forces on these diagrams. In my examples there, I have 10 examples there. The first one is just regarding a book at rest on a tabletop. Again, surfaces you can draw on a free body diagram, but in order to draw this free body diagram, really what's acting on it? Well, for number one here, here's my object, there's my book. It's either a square or a circle. Make it very simple. But a book is at rest on a tabletop. What's acting on it would be my force of gravity. Okay, force of gravity. And something's obviously preventing it from accelerating through the table, and so that's going to be my force normal. In which case these are both going to be equal. Number two, a gymnast is holding two ropes and they're motionless above the ground. Again, there's my gymnast, nice square. Gravity's pulling down on her, and the force of tension of one rope is pulling up, as well as the force of tension in the other. According to my diagram here, if this was stationary, these two forces add up to be the same magnitude as that force. Okay, number three, an egg falling from a nest in a tree. You could draw a circle for an egg or a square, but there's my egg. What's acting on it is going to be my force of gravity, and that's all that's acting on it. We're ignoring air resistance, so that would be it for number three. What about the other ones there? Well, we can look here and say a tissue falls at a constant velocity due to air resistance. This is a little different because we're adding air resistance. So in the last example there was only force of gravity. In this one there'll also be force of air resistance. I'm going to call that a force of friction instead of force of air resistance. It's really air friction that's causing it. And if it's moving at a constant velocity, these arrows should be the same in length. Number five, a rightward force is applied to a book to move it across a desk. Okay. It doesn't say anything else here, but it says that there's a rightward force. Let's say that's a force applied. We know that there's a force of gravity here, and there's a force normal. Now force normal and force gravity will be equal to each other. Force applied could be here. Because it doesn't specify in its example whether there's friction or not, I'll just assume that there's friction. Okay. If these were equal, it would be moving at a constant velocity, okay, or it would be at rest. If force applied was greater than force of friction, then it would be accelerating in the right direction. If force applied was less than force of friction, then it would be slowing down. Number six, a force is applied at an angle of 45 degrees above the horizontal to the right to drag a sled across loosely packed snow with a rightward acceleration. Okay, a lot in there. Here's my sled. Here's my force applied, and this is at an angle of 45 degrees. Okay, above the horizontal. And so I'm applying a force. It's on snow, so I'm going to assume frictionless. There's definitely a force of gravity here, and there's a force normal. Note that I can break this up into components here, and I'm going to say, you know what, let's call this FAX and this FAY. Force applied in the y direction and force applied in the x. If you look at the way this is drawn here, again, you don't have to include the components. In fact, a pure free body diagram would not include components, but I'll do it here because it's useful in solving problems. At 45 degrees here, you'll notice that this is the only component here that's actually making it accelerate to the right. And in fact, what I'm pulling up and the normal should be equal to gravity, so this thing doesn't accelerate up or down. Number seven, a football is moving upwards towards its peak after being booted by the player. Well, in fact, if we're ignoring air resistance, my football, the only thing acting on it is gravity. It's always down, even though it's moving upwards and to the right. You know, it could follow a path like this. Even though it's doing that path, this is my only force acting on that object. Number eight, a car is moving to the right with its brakes applied. So here's my car. There's obviously a force of gravity acting on the car. It's not falling through the road, not accelerating, so there's a force normal. When you're applying the brakes, you're not really having a force applied anymore. And so because of that, I don't need to put applied force. There's no gas pedal. You don't push them both at the same time. So there really is only a force of friction. In fact, that's my net force, which is the reason why if I'm moving this direction, I'm slowing down, because my net force is in the opposite. Okay. Sorry, that was number 8. And number 9, a block is at rest on a sloped frictionless surface. It is prevented from sliding by a compressed spring at the bottom of the slope. A little awkward. I'll just show you what this means. If I have a picture here, here's what the picture looks like. There's a block. It's prevented from sliding because there's a spring right here. Okay, and I'm attached to a wall here, but there's a spring. So this is what it looks like. What would the free body diagram for that object look like? Well, if I'm going to draw it here, okay, there's a force of gravity acting straight down. There's a normal force pushing this direction, okay, outwards. There's a normal force. And the spring itself would be pushing up. I'm going to call that force of the spring. And it's frictionless, so those are my forces. This would, of course, be in equilibrium, and all these would cancel out to give you 0 net force. And the last one there, a heavy box is being slid across the floor by 2 people. One pushes it to the north, while the other pushes west. The difficult thing that people have in this problem is they want to show force of gravity and force normal. And you can do that because it's on a surface, and you can say, well, they're equal. The problem is west, north, south, east. It's hard to show that on a 3-dimensional diagram. So I'm going to leave off up or down and only include west and north. And in fact, I'm going to show this as this way and this way to being north and west. So this is the force applied, I don't know, by person 1. And this is the force applied by person 2, let's say. But understand here, I'm not showing up or down motion. I'm not showing force of gravity because I can't do it on the same diagram that I'm doing north, west, east, south on.